Shiloh pool, and then through the newly discovered tunnel going back to the Davidson Center. So this is a dry route, although those of you who are brave enough could go to the water, Michael, if you are willing. It's going to be very cold, but it's going to include a walk of about 600 meters through a tunnel, so maybe some of you will not be so comfortable with that. But you can walk standing up. We just need to know how many people are coming, so if you can sign your name if you're going to join the trip at the registration table. Okay, and now back to science. So it's a pleasure to have a Michael with us. I think that many of you already experienced maybe the disappointment that when you have a very good, brilliant idea and you think it's going to change computational biology, and then you go and look it up in PubMed and you see that there is a paper by Michael from the 80s, sometimes the 70s, that already described it. So really, what's better than to start with one of the pioneers of the field, Michael Levitt, please.
Thank you very much, Michal, for letting us be in this institute. I think I was here maybe not 18 years ago, but quite a long time ago. You said you were a student and you came and listened to me. So, it's a good thing you warned me about the room, because I was about to say how fondly I remember the room. But then I looked around. It is a brilliantly designed room. There's a PowerPoint under every seat. And those of you who know how I am in lectures realize that that is important. At Stanford, we built a very fancy new building for an incredible cost, and they decided that they were going to put in internet points everywhere, but no PowerPoints. And I said, but there's something called Wi-Fi. They said, oh, but there's also something called batteries. And I guess it didn't work out. Roger, too, I wanted to thank you for calling me a scientific grandfather, because as you know, there's nothing I'm more proud about than being a grandfather, but particularly in Nir's case, Nir actually did his PhD with Chen Kesar, who was my postdoc. So Nir, in a very real sense, is a scientific grandchild, and yesterday I had the pleasure of meeting his parents, so I guess it all comes together. Give me a second, I'm just going to set up my... While I'm just setting this up, I am definitely going on the trip. I'll be bringing sandals and a swimsuit. So, although sometimes the coldest water I ever went into was in a pool in the Negev desert, in a place called Ein Akef, and the water was 6 degrees centigrade, and that's actually kind of cold. Anyway, okay. So today I'm going to give the first of 2 talks, and this one's going to be about methods for simulating macromolecular complexes. This is going to be somewhat of a historical survey because a lot of things have been around for a long time, and hopefully we'll get to some of the things we're currently doing. So basically I'm going to talk about physical principles and forces, simulation methods, then go into normal modes, which are a topic which have not received as much attention as, say, molecular dynamics, and a little bit about newer methods, and then just a little bit about the future of simulation. There'll be a lot of movies that hopefully will work. So the problem basically is if you have a beast like the ribosome, say 200,000 atoms, as many chains as small proteins have residues, so you've got something like 67 chains, how do you deal with a system like this? And this has actually now become a major focus of my lab, but we are still in a situation where I'm not prepared to talk about it yet. The ribosome is a very difficult area because there's a major following in a field, and you don't want to open your mouth until you're quite sure that things are okay. But this is why we're doing what we want to do. We want to take a system like that and see it working. Now, on the path where we've looked at easier systems, we've looked at RNA polymerase that Roger has worked on, which has only got maybe 30,000 atoms, or maybe 40,000 atoms, but still is a very, very large system. And this is because biology seems to be done by machines that have moving parts. And it's not, I mean, early enzymes would catalyze a reaction by electrostatics or electronic effects, but nothing sort of moved. Well, the products moved away, but there weren't any big moving parts, and it's clear that large-scale movement is intrinsic to this problem. Okay, so a little bit about physical principles, because this is something you should all know, but I constantly find myself being reminded about it, and that is that almost everything we see in biology involves going from one state to another state over a free energy barrier. So this is just a one-dimensional, in this case, potential energy, but it could be a free energy, where you have a state here and a state here, and basically Boltzmann's principle just tells you how much of your population will be in state A or state B. And essentially, what is hard here is not this, but the fact that you have to normalize so that your probability is equal to 1. And that means summing this thing up over all states. And since there are a very large number of states, it's the partition function that gets you, and it's just a normalization factor. Okay. Another thing that's really important is that most things that happen are not simple vibration. I mean, you can actually see here you have we'll talk more about this. If you have a minimum like this, you can vibrate around the minimum in the same way that a spring vibrates, or something would break. If you had a surface shaped like this and you let a ball loose, it would vibrate about the middle point. Much of motion in biology is not vibration, it's stochastic motion jumping from one state to the next. And here the key equation is that the time it takes to jump from state A to state B depends exponentially on the free energy height of the barrier. That means if you increase the barrier by a factor of 2, the time is squared, a huge increase. Okay. And just finally, just to give you some idea of, in biological systems, there's an incredible range of motions. The fastest motions would be bond stretching vibrations. That is a period of about 100th of a picosecond. So that's around 10 femtoseconds. That corresponds to 3,000 wave numbers. And then you go all the way down, water tumbles in about 20 picoseconds. In fact, as a very rough rule of thumb, a molecule with molecular weight m tumbles in m picoseconds. It's kind of amazing. You can actually you can show that basically there is a temperature between 0 and 20 degrees centigrade where that is exactly true for any molecule with the fusion constant changes a lot. And then you have things like protein folding that take maybe 10 to the 14 times longer than a bond vibration. Now, the things that are quick, less than about a picosecond, are periodic vibrations. Things that are slower are stochastic jumping over barriers. Okay. So it's key for all of this. I kept on talking here about an energy function. This is the potential energy function. It's key for all of studies of any molecule to have a potential energy function that describes the potential energy as a function of the position of atoms. And this was essentially the big breakthrough that happened in the late 60s in Schneur-Lifton's lab with his then PhD student Arya Varshil, who I'd hoped would be here but isn't. And Arya basically helped develop a potential energy function for hydrocarbons, basically aliphatic hydrocarbons. It turns out that they divided this energy function in a way that they called consistency. What they really meant was don't have too many parameters and think really carefully about your choice of parameters. So the energy function essentially looks like this. It is a classical energy function. It's very easy to think about its terms. Bond lengths and bond angles are just harmonic springs. The energy function is just simply harmonic function or quadratic function. When you stretch the bond length, the energy goes up. When you compress the bond length, the energy goes up. Same thing is true for bond angles. Then you have torsional terms. If you rotate around a torsional angle here, or a dihedral angle, the energy will go up and down and come back to itself, because when you've gone around 360 degrees, you're back to the beginning. That's a periodic term. And then you have a term, van der Waals term or Leonard-Jones term, which allows for the fact that when two atoms get very, very close, they repel each other. At intermediate distances, they attract each other. and then far away they don't care. And then the most complicated term is electrostatics. Like charges attract each other, unlike charges repel each other. And that's very, very simple. And what Lifson and Varshall had done was to find a way to determine these parameters. The parameters, these energy parameters, in their case, were determined from experimental measurements on small molecules. In general, the parameters can't be determined directly, so what you need to do is take an energy function like this, use it to calculate lots of different properties of small molecules, crystal packing geometries, crystal packing energies, strain energies, vibrational frequencies, etc. Compare these with the measured values, and then in a least squares fashion, change these energy parameters. So that's essentially what happened. Now, what is surprising about this is not that it was developed in the 60s, but that it's still being used. And in order to bring that point home, I put the names of the people you can associate with these terms from Hooke, 1635, to Coulomb, 1736, and then call this the dead physicist energy function. And this is to annoy my friends who still think that this is the absolute state of art in calculation. What is true is that probably half the non-military computer power in the world is used evaluating this equation in doing dynamic simulations. It's kind of amazing. And maybe it's not a half. Occasionally I think about the carbon dioxide footprint and it's kind of scary. In any case, this equation is extremely simple. Over the years we've refined how the parameters are determined, but they're still sort of determined by fitting experiment. It allows you to describe the potential energy of any system. Now, one of the nice things about physics, and I studied physics, and I guess, is that you have lots of shortcuts. In physics, you get a lot of stuff for free. And one of the things you get for free is that if you have the energy function, potential energy function, you can calculate all the motion by just taking it from there. And there are a number of commonly used methods for getting motion. One is just energy minimization, the simplest. You start at a high energy place, you drop down to a low energy place. That's important if you want to know whether there's a stable minimum near where you are. So you drop down. Another nice thing about physics is that what works in one dimension also works in n dimensions. So there we have a two-dimensional surface. Then we have something that I call normal mode dynamics or vibration. And that's where you have a minimum like this, and you vibrate about the minimum. I'm actually stopping it, but it could go on forever. And the same thing is true in two dimensions. So these are normal modes. Then you have something that I've called molecular dynamics, which is very well known, where it's a bit like minimization, but now you keep thermal energy, so you go over barriers and things will keep on moving except I stop the system. And then the most recent technique, the simplest, but perhaps also the most interesting, is Monte Carlo, and that's where you just jump about at random, and if you go to somewhere where the energy is lower, you accept the move. If you go to somewhere where the energy is higher, you sometimes accept the move. Again, you can put names on these, and these are the dates of birth, if you like, of the senior, of the first authors. This is the most interesting one, because this is Metropolis, and there's a very famous paper from 1955 or 56, which has got authors Metropolis, Rosenbluth. There's two couples, and then Edward Teller, who was the father of the hydrogen bomb. And this method was instrumental in allowing for neutron diffusion in making hydrogen bombs. It's incredibly simple, but as computers have become more and more powerful, it's more important. These methods, this method requires first derivatives, these two. This requires second derivatives to get the curvature. This just requires a move set and jumping around. Okay. So let's first talk about simulation through molecular dynamics. This is now the most used part of the energy function. And basically one uses the same energy function, one takes the forces and calculates, takes the energy and uses its first derivative just to get the forces. If you have an energy function, then the slope of the energy function is just the force. So now what you do is you want to calculate motion. It turns out that calculating molecular dynamics motion is extremely simple. It turns out it's extremely simple, but this is also very, very difficult to do properly. So if you have more than 3 particles, there's no way to calculate what the motion is going to be analytically. The equations are just too sensitive to initial conditions, and you get chaotic behavior extremely quickly. And this is extremely important actually for other reasons, but it turns out, although the exact analytical solution is impossible, a numerical solution is trivial. And a numerical solution is very easy to understand. each particle thinks that he's the only one moving. Now, if all these particles are stationary and this particle is moving, and he only moves for a very small distance, he essentially moves under constant force. And under constant force motion is incredibly simple. It's basically a particle falling under gravity, an apple, or whatever you like. And it turns out that the equations of motion that are actually used in the calculations are a small variant of that. So if a particle were to move just under gravity, the new position is the old position plus velocity times time plus half the acceleration times time squared. That's something which I guess is learned in high school. Turns out in fundamental dynamics you have to go slightly more complicated because in fact the other particles are moving. And the force is not actually constant, it's changing. So what you need to do, the equation for the new position from the old position is velocity times the time step, plus a term which you can see if the accelerations was constant would just come out to 3 divided by 6 would be a half acceleration times time squared. So this term allows for a small correction. The velocity again is calculated, but these are the equations that are actually used in most programs. People early on tried much more complicated integrators that were higher order, didn't actually work very well. Now, so you have, given a position of the system and a set of velocities, you can get a new position and a new velocity. The problem is that for this whole story to work, the atom has to move a very small amount. And it turns out it has to move something like 10 to the minus, has to move at normal temperatures for a time of about 10 to the minus 15 seconds. For a great deal of effort, you can maybe go to 3 times 10 to the minus 15. Maybe with a super amount of effort to 10 times 10 to the minus 15, but it doesn't make any difference. And the point about this is that if, say, you want to simulate, let's just say, 1 microsecond of some reaction, this means you have to iterate this equation 10 to the 9 times. So that is already very scary because it's a numerical approximation. Your time step is as large as it can be. So are we doing the right thing? And it turns out that, again, just very, very simple mechanics comes to our rescue. Atoms have velocities. They also have masses. So they have kinetic energy, just a half mv squared that you get from gas theory or anything. And that actually ends up being equal to the temperature through the Boltzmann constant. But more importantly, the total energy, the potential energy, which is what I showed here, which is going to be changing with time, plus the kinetic energy shown here, should not change with time in an isolated system. So if it's changing with time, there's a computer error. And early on is sort of late 70s, early 80s, this was a really important way to get the programs to work. So energy conservation is still an important test. Okay. So essentially you can simulate motion, and I forgot a slide here. I meant to insert a slide mentioning Aniso Raman. Raman is a physicist at, I think, Argonne, no longer alive, but he, in the 50s, did molecular dynamic simulations of liquid argon, and then together with Frank Stillinger, did simulations of liquid water in the late 60s. And essentially what they did is they used these equations with an energy function for water that was actually more complicated than what is used here. And nowadays water has actually become simpler, but essentially it was a water molecule with 5 points, a center oxygen, and then lone pair orbitals and 2 hydrogens. So it's a little bit more complicated than H2O, but not much. And then they showed, amazingly, that if you took a bunch of waters, put them into a box, and ran simulations, you actually got a system which correctly produced almost all the properties of liquid water that you could measure. Here's just an early calculation that we did. We did a lot of calculations on water. It's just a movie showing what the waters look like in space filling and in stick pictures. The reason I'm showing you this is that it's really hard to see anything because the eye is very attracted to a high-speed motion. So what you need to do is do frequency filtering where you remove the high frequencies, essentially by just averaging adjacent frames. That's exactly the same thing with the clock going at exactly the same speed, just taking out the high frequency motions. And suddenly this looks like a bunch of birds on a summer evening. You can actually see what's happening. You'll see it in space filling. You can actually really see what the systems are doing. This is a very important thing to do. You can see hydrogen bonds being broken and reformed in cavities, etc. Okay. So this ended up being important. And the reason is that when you run a simulation like that, So the simulation, once you've got it all set up and your programs are debugged, just requires computer time, a lot of computer time. As I said, the amount of time you can simulate is just linear in how much calculation you do, and you want to run long simulations, you want to do a lot of sampling. Now this is good and bad. The bad part is, how do you then analyze all that data? And in fact, today, a problem that has not been solved is how you consistently and cleverly analyze molecular dynamic simulations. People do it in a piecemeal fashion, but anyone who has not actually tried to do it just cannot be familiar enough with the problem. When people talk now about big data, maybe they should first solve this problem before. I guess it's much easier to solve what you're going to buy when you go shopping than exactly what this is doing. And I used to joke saying that you run a simulation, you get 100 gigabytes of data, and what you want to do is reduce it into 3,000 words. And that is very difficult to do. Okay, so let's just now move. Now, if you can run water, it turns out that because of Lifson's and Varshall's simple parameterization, it was relatively easy to introduce other atoms. So for example, even simple things like, oh, oxygen is bigger than nitrogen. Nitrogen, oxygen, hydrogen bond. Hydrogens attached to nitrogen generally are positively charged. Very simple rules like this could lead to an energy function that could be applied to a whole protein. So I was doing calculations like this in the late 70s, and again, the problem was to analyze them. There's one device in analysis that physical chemists love, and these are correlation functions. Most people who are not into that find these very difficult, because they always are just decaying exponentials, and it's very, very difficult to see what's going on. But movies are very helpful. So this is the first movie made of a simulation. It's actually made at the NIH by Richard Feldman. Each frame took a day on a major supercomputer, and they're 24 frames a second. To give you some idea of how difficult it was to do the algorithms, the person who actually drew shaded spheres went on to become one of the founders of Pixar, which is now this massive animation company and probably got really, really rich. Now, here's a protein. Now, what's interesting is if I ask you, what does the motion look like? So, there's nothing that really looks like this. Sometimes you see these pictures of a bag of worms. They're worms that sort of form bags. And they sort of look like this because what's happening is everything is moving. No one's really going anywhere except this water molecule which has been expelled. And they're not really moving according to a nice rhythm. So maybe it's like a funny shaped disco viewed from the top that's very crowded and really difficult music to dance to. So everyone's just moving randomly. But this, I think, is still a very accurate picture of what a protein motion would look like, both in vacuum and in solution. Now, these calculations were actually done in vacuum. Turns out that real proteins are surrounded by water, and although waters had been done before by Raman and Sillinger, getting the waters from Raman and Sillinger to merge with protein calculations was actually very difficult. It's something that I devoted about 8 years of my life doing, basically when I was at the Weizmann Institute here in Israel from 79 to 87, and together with Ruth Sharon, who was a close collaborator in that period, we did the first simulations of a protein in water. Now, these calculations were really expensive. The only reason we could do them was because we got a grant of 200 hours of Cray XMP time for the National Science Foundation in 1986. Each hour of computer time was $1,000 real dollars. So $200,000 of computer time is at least $1 million in today's money. And what it allowed us to do was to run a small protein bovine pancreatic trypsin inhibitor, 58 residues and 1,001 atoms, including the hydrogens, for 200 picoseconds. Nowadays, you could probably do that on your iPhone in almost in real time. So this was a very difficult calculation. And the end result is shown here in this curve. So basically, when you ran simulations in vacuum, and it doesn't really matter who ran them, things moved a long way from the starting point. This is the deviation from the X-ray structure. Things moved a long way out to about 2.5 angstroms. And initially people said, oh, well, it's not surprising. Isn't the crystal constraints? Who cares about the crystal structure? But when we did things in water, it was very clear that things remain much, much closer and run for a long enough time. And nowadays, almost all calculations of proteins are done in water. So I'm just going to show you a couple. My first postdoc, Valerie Daggett, did a calculation. And this is actually a protein unfolding in water. So firstly, if the calculation is in water, you don't actually see the protein. So we're slicing through the box, like through a block of cheese. There's the protein. And all of these movies are actually like vintage movies. They were all made in 1990 and were quite difficult to make. And here it's moving, and I guess it's moving. These are ions drifting around. We've taken out the high frequency motion by frequency filtering. Things are moving, but it's still, again, movies are nice, but it's really hard to see what's happening, other than the fact that the ions are moving. When the ion leaves the box, he actually comes back on the other side, so we're not going out anywhere. At some point, we have actually jumped the temperature. Now we're going at much higher temperature. The waters are moving like crazy, and the protein is actually becoming a molten globule. Interesting. Turns out that early on, it was relatively easy to do proteins in water. What was really, really difficult was to do nucleic acids in water. And the reason is that DNA is not really a globular structure. Here's a picture of DNA with its 2 strands. And essentially, I'm going to have to change my batteries, or maybe I'll use a different pointer. So basically, here you see the DNA sliced through. There are 2 strands, and you have these phosphate groups that carry very strong negative charges. So DNA without the counter ions blows itself apart. DNA in vacuum, proteins in vacuum, only stay within 2 angstroms of where they should be. DNA in vacuum jumps up to over 6 angstroms from where it should be. In water, DNA is also quite stable. So doing the calculations in water were very difficult. They were done by Miri Hirschberg, who was my first PhD student, 1997 to 1990 at the Weizmann Institute. And here's a movie, of her work. So again, we have a big box of waters. We slice through it. We see the DNA inside. The DNA is going to start moving. And the basic bottom line is it's not going to blow apart. So that was important. But actually, interesting things do happen. Bases break at the ends of the strand, which is something that's known. There's actually an AT base pair that breaks over here. There's lots and lots of counter ions, and they move around. Okay. So let's move to the other kind of simulation, the one involving normal modes. I'm going to have to speed up a bit. So basically, normal modes is sort of like the complement of molecular dynamics. In molecular dynamics, we have exact equations of motion, but we solve them approximately. In normal modes, we assume that the energy function is a quadratic function, a basin. And once we have the basin, we can solve equations of motion on a basin exactly. So in one case, we approximate the motion. In another case, we approximate the energy function. And this complementarity is interesting. Basically, normal modes are just like the vibrations of a string or a pendulum. Strings will have different levels of modes depending on what's happening. And the nice thing about normal modes is that if you can think about them in one dimension, you can also think about them in any dimension. Here is a generalized energy function, and at any minimum, the energy looks like a basin. Any minimum looks like a basin. Vibration about that basin can be done by the same equations of motion. This just shows that in a normal mode, you move across these axes of the ellipsoid in different ways. Okay. Again, this energy function we would like to use, but we're going to do the calculations not in Cartesian coordinates, but in torsion angle coordinates. The reason is that early on, large matrices were very, very difficult to do in Cartesian coordinates. In computers, they required large amounts of memory, which didn't exist. In torsional space, it was much easier. So essentially, we don't need bond terms and bond angle terms. We just use these terms. And then we can basically write down a much simpler energy function, which just has the torsional terms, the Leonard-Jones terms, and the electrostatics. And now we have a quadratic potential. It turns out to be very easy to solve the equations of motion. There's a way in which you can write these down in a symmetrical fashion where you have potential energy as a quadratic expansion of the positions and kinetic energy as a quadratic expansion of velocities. This is a generalized mass tensor because in torsional space, mass is not a diagonal object. Turns out you can solve these equations of motion and get normal modes. Essentially, it involves solving an eigenvalue equation. This is something we did in the mid-'80s. And what was interesting when we did this was we found that if you look at different frequencies, so now once you get the normal modes, you get different frequencies of motion. You can separate them out. And what you find is that the almost torsion angles move about the same amount no matter what the frequency is. But the actual backbone is only moved by the low frequency normal modes. Low-frequency modes move a lot of matter. High-frequency modes are moving everything. The torsion angles don't really care whether they're moving a lot together or just small motion. So again, let's go to movies. Here's a very early movie, again made in the early 80s of BPTI. This is one of the very first drawings of this sort of ribbon diagram, actually drawn by Arthur Lesk. And this is just showing, so this motion looks very different from the dynamics of the same protein that I showed you before. It kind of, people like normal modes. They kind of feel relaxing and rhythmic, and maybe you could have a meditation application that actually had normal modes, and you, depending on what frequency you felt like in a particular day. Okay, so I'm going to skip, well, let me just show you lysozyme, which was another system that we studied. In lysozyme, there's an active site. The site is blocked by the substrate. When lysozyme starts to move, normal modes basically sort of show a closing of this mouth. So in some ways, and again, this is a 1970s thing, lysozyme movies look a bit like Pac-Man, which has actually come back again, and you can play it on your iPhone. So here is its mouth, and this, so it looks like in some ways this flashing of a tryptophan is a bug in Arthur Lesk's program. That atom just disappeared sometimes and came back again. Okay. So let's now go one step further, and that is a very important part about simulation, is to try to get rid of details. This is something that I did with Arya, again, in the mid-80s. Basically, we just simply said that in order to fold a protein, throw away 90% of the atoms. We used a very careful physical justification of why we could do that. We said that there's a chain and there's side chains, and instead of worrying about the particular nature of the atoms in the side chain, we could treat it like a lollipop. But it turns out that nowadays you can basically completely cheat with knowledge-based potentials by using what are called knowledge-based, but with coarse-grained potentials, by using what are called knowledge-based potentials, just look at all of the structures in the protein data bank and just simply ask, what is the distribution of distances between any atoms of interest? So for example, if you're interested in the OD1 of aspartic acid and the CD2 of phenylalanine, you can just histogram what the distances look like. And then you can normalize by what you'd expect for some random model and effectively get a potential of mean force. It's just a probability, take a log of the probability, you have a potential. This has been used a great deal. It was first used by, as I say here, Tanaka and Shiraga in 1976. Early on it was very hard to do because there weren't enough structures. Now there is a lot of structures. And I'm going to just skip that, okay. So you can actually, we'll just go back to here, you can replace the energy functions by quadratic splines or quintic splines. So you approximate the energy by what you'd observe from these histograms. Okay. So we would now like to move on to meso-scale machines, and I'm going to start off with normal modes. So we're going to start off with myosin. Here's just a movie of myosin morphing. So myosin has two states, and we're just going from one state to the next by interpolating between the states. I use a program that was developed in our lab by Dalia Wife called Climber. There are many different ways of morphing, and for making movies it really doesn't matter which one you use, and I think if you really care about it, they're all about equally bad. So this is one way of morphing. You can also morph in a different way, which is what I call rigid body morphing. So now we're just taking complete rigid bodies. And what's nice about rigid body morphing is that you start to see that the movement of the arm of myosin is actually coupled to movement of the body. And the ATP side is over here. So this suddenly indicates, basically because everything is rigid, you amplify the motions. If everything is flexible, like I showed you here, although the exact chain, oops, maybe now I can see it. See, it's very hard to see that. Well, you do sort of see it, but not in the same way. So rigid bodies are a great way to amplify functional motion. Okay, here are normal modes on exactly the same system, and basically you see it's sort of the same. It's much smaller. This is the normal mode where we've used all the atoms. We can also do normal modes where we use just 3 atoms per residue, which we call the 3-point model, and essentially they're exactly the same. Or even what we call the 1-point model, just 1 sphere per residue. Again, in every case, the energy functions come from knowledge-based terms. So they just come from what distances are observed in proteins. Now this can immediately be generalized. So we decided maybe 5 or 6 years ago, actually a bit more now, to simulate cellular machinery. So here is all of molecular biology on one slide. Inside the nucleus we have the DNA packed around histones in nucleosomes. We have RNA polymerase, which Roger solved, copying the red DNA onto a blue RNA, which then comes out of the nucleus. The ribosome, which was solved by Adi Ornat, Tom Stites, and Venkat Ramakrishnan, and others, is then used to take the RNA and make proteins, and proteins are often helped fold by chaperonins. So I thought, well, let's just take the structures that we have and calculate normal modes. The normal mode calculation, unlike the MD calculation, take a few hours on a laptop, even on really big systems. They require very careful programs. It turns out that the programming for normal modes is much, much harder than the programming for molecular dynamics. Here are some normal modes of a nucleosome. The DNA is wrapped around the outside. These modes, when I describe these modes, I simply say that they're suggestive. And in English, suggestive has a lot of different meanings. And these are motions that maybe help people think about function. Maybe this helps you think about the DNA coming off the nucleosome. Okay, here is the ribosome. This is a very early simulation of ribosome modes. I'll show you another one. And you can sort of see that the small particle moves relative to the large particle. Okay. Here is motion of a chaperonin, a bacterial chaperonin, which is meant to enclose an unfolded protein and make it fold. Another one, a eukaryote chaperonin, which I will be talking about in my second lecture. Okay. Now, this all looks good. Now, how do we tell it's good? So we take molecules of all different sizes, from 74 to 1,052 residues, different amounts of protein and nucleic acid. So the first thing we do is these modes are calculated by starting out from the X-ray structure and minimizing. And we are able to find really good minima within a few angstroms, worse for myosin where it's 4 angstroms, but even for the ribosome, we find a precise minimum in torsional space, 2.4 angstroms from the X-ray structure. That actually is very difficult. Finding a minimum in a high-dimensional space in torsional angles is not easy at all. I'm very proud of the program. Okay. Turns out, though, everything was not as simple as one would like. Here is RNA polymerase done early on, and it makes no sense at all because there is one chain in RNA polymerase which is draped all over the molecule, and it's moving like a rigid body. Now, why should a chain move as a rigid body? This chain is obviously very heavily attached to the parts around it. There's something wrong. And the problem is that when you do normal modes in torsional space, you care about the order of the chain. You start at one end, and you keep on rotating until the other end of the chain. But the order of entire chains in a PDB file is totally arbitrary. And this particular red chain that behaves so strangely actually is the last chain in the PDB file. Something is wrong. And this is a very difficult problem. And the problem is basically that there's a kind of chain order paradox. So what we did is we would take a PDB and put in dummy atoms in between to link them all together, because we wanted everything to be linked together. This does not work, because in this case, depending on which one is first, here this is at the end of the chain, you could have gone in this order. The order is completely irrelevant. It depends on how things are stacked into the PDB file. So what you need to do is something like this, where every single molecule is connected to the origin by 6 degrees of freedom. And it turns out that it's not trivial how you do this, but it can be done because everything has to be continuous and differentiable and commute, etc. But when you do this, suddenly everything behaves really well. Picture. Now, the trouble is that if you now go back and try to solve the eigenvalue equation, when you have independent bodies, it just turns out that the potential energy matrix often is singular, which means that if you move the entire structure, its potential energy doesn't change because all the distances are the same. The kinetic energy matrix is usually not singular. But once you have independent chains, it is singular. And this is a major problem. You need to solve this particular eigenvalue equation where both of these matrices are singular. Turns out that none of the packages do this. I was amazed. And this must be a very common problem, but no one seems to care about it. So basically, I tried various different packages. None got it right. In the event, I found a hack to get it right, and I'm not going to go into it. We managed to get it right. More recently, I've been in touch with a numerical analyst at Davis, and he sent me a correction that he says would make it work. I haven't had a chance to test his correction, but anyway, this basically works, and it involves generalized inverses and stuff like this. Is sort of an old way of doing it, but I'm not going to go into it. Okay. So basically now things are working. The eigenvectors are always real. Solutions are always obtained. It's totally insensitive to singularities, and it's also insensitive to round off. It's very important that you have these properties. Once you do this, you can now take a symmetric system. Here is a system of 87, I think it's actually, is it 87? Maybe it's just 60. I forget now. It's a small tetramer, perfectly symmetrical. And when you look at the modes are now perfectly symmetrical. And that's because there's no one that's first. If you chain them together, you don't go that. Skip this. You can now go back to RNA polymerase, and it makes perfect sense. The red chain is now draped around the back, and everything is fine. Okay. So using this method, we have now moved on in sort of a jump in generations. What I was showing you there was probably 5 or 6 years old. It's something which I sort of did myself, and therefore writing it up is almost impossible, but I'm going to force myself to do it in the next few months. Here is a normal mode of the entire ribosome. In this case, every single atom. So here's a normal mode of a structure with 200,000 atoms, the same structure with one point per residue. And basically, there's a lot of the motion here which we're now realizing is significant. Here are the tRNAs. It just shows that you can do a calculation like this, and that is, in fact, no mean feat. Okay. Other newer methods involve Markoc state models. The key thing when you deal with very large systems is to reduce degrees of freedom. One very easy way is to say, I say to somebody, we'll simulate my arm moving. Now you could say we're going to take 10 to the 26 atoms, or whatever number, probably less than that in my arm, some number, 10 kilos of atoms, and simulate the molecular dynamics for a few picoseconds, or maybe a few billion picoseconds, and then decide the motion. Now all that's true. I mean, everything is actually moving in my arm. But you don't really care about. What you really care about are key degrees of freedom, my elbow, my twisting, etc. You can pretty represent an arm really well with 10 degrees of freedom. So can you represent these large systems by small numbers of degrees of freedom? So this is some work that was done by Shui Hong and Daniel Silva. It actually involves RNA polymerase. This was a collaboration that also involved Roger. We took the structure that he'd worked on, or Shui took the structure that he'd worked on, put it into a big box of waters. Which is shown here. Let's skip that. Here's the thing in a big box of water. And then we're going to simulate the motion of a system of almost 500,000 atoms, including all the water. Now, there's no way you can simulate a system like that for a lot of time, even with huge amounts of computer time. So what we did was to essentially cheat. We used a technique that has been developed in robotics called probabilistic roadmaps. And basically, in robotics, if you want to go from one state, say, of your scanner to another state, you don't want to bump into anything. And the way they do this is they basically just fill the space with random points and ask which points are feasible. And then they say, let's make a pathway between feasible points. If they're close together, it's very unlikely that you're going to bump into something when they're very close together. You do exactly the same thing in molecular space. You have points which are allowed because they don't form collisions. And then if you want to move from here to here, you already know that you follow a path like that. Exactly the same thing can be done for a much more complicated system. Here's a movie, and as the movie goes on, I'll tell you exactly what we did. But essentially what you do is you run many, many simulations that are along the pathway that you're trying to simulate, and then join them up. In this case, we ran almost 1,000 simulations. Each one took a large amount of a major supercomputer, but they could be run completely in parallel. So as long as you had total cycles, you could do them. It's a method called Markov state models. And here is the movie, which I think is particularly nice. It was made by Daniel Silva, who was Shui Huang's PhD student, and I guess he's another scientific grandson because Shui was in my lab. So here you're seeing movement on a very, very rapid time scale. These are microseconds, and this is just because you're jumping between states. These are not vibrations. You create a state space and then jump between states. But the motion is sufficiently complicated that really allows you to see what's happening. Here is the RNA polymerase. The blue strand is the DNA. The green is the lagging strand of the DNA. The red is the growing strand of RNA. And in this system here is the bridge helix. On this helix here, the bridge helix, is a tyrosine which interacts with the base that needs to move from here to here to act as an elongation template for the RNA. We're just going to see that motion. Again, these are random snapshots, but then later on selected to give us this pathway. Getting stuck. Finally, it goes all the way. And if we stop the movie here, we now have an unpaired nucleotide just waiting for a nucleotide to come up through the tunnel and base pair to here. So we start to understand the mechanism in some detail. The actual state space is quite complicated. This is what the actual state space looks like. What we did is we started out with a form, and we basically just took the RNA and moved it forward by one base pair in 1,000 steps. And then around for each of these steps, ran simulations, analyzed this very complicated graphical object. At every point, we have a free energy. And I guess what's good about this is that it forces you to look at your data. Whether you like it or not, you've at least got to look at 1,000 states. Whereas sometimes in simulations, most simulations involve the same graph that I showed you for DNA early on. The RMS deviation is a function of time. And that is a great way to check that your program is okay, but it's not necessarily a great way to understand the system. Okay. There are other methods. There's a method of Monte Carlo, which we call natural move Monte Carlo. I was always very reluctant to use Monte Carlo methods because they seemed incredibly wasteful. But a postdoc in the lab, an ex-postdoc, Peter Minari, developed a very, very nice Monte Carlo method that we called natural move Monte Carlo. So as I said in Monte Carlo, you can basically make any move you like. But the kinds of moves you'd like to make on a molecule might break the bonded structure. This is particularly true for nucleic acids. So let me try to illustrate that. So here is a piece of double helix. And the moves we'd like to do are just to move the bases around and not really care about the rest of the structure. The trouble is, because there are two strands here, if you move the base in a certain way, you're going to break the chain. So Peter developed a very clever method to close the chain connectivity. So you make a move, essentially analytically you close the chain connectivity, and then you continue. You can then make moves hierarchically by moving entire helices, but the important thing is that you can sample the space of RNA very, very effectively. Here's an example of an application where they basically, Adeline Sim, who was a student of mine, with Peter, Adeline, with Peter, basically did the calculation where they took RNA that could form a square structure and showed by this method how much fluctuation there was in this angle, and so on, and could even look at mutants. But this is a very large RNA structure. The great thing about the method is that your degrees of freedom could be the movement of an entire helix, the movement of a base pair, combination of them, so you can have moves that are on different scales and they all work together, and Monte Carlo takes care of them all together. Okay, so a little bit about the future of simulation. So I guess, since simulation started about 60 years ago, say with the work of Raman, we have probably more computer time than that. We probably have 10 billion times more computer time. 10 to the 10 more computer time. So you might want to ask, how is that time being spent by the community? So what's really interesting is that the systems are larger, maybe 100 times larger. A water box that was done by Raman and Stillinger was 216 atoms. Calculations 100 times larger, maybe even 1,000 times larger, are fairly common. 1,000 times not so much, but 10 times very, very common. Runs have become much, much longer. So almost all the computer time has been spent in doing longer simulations. What is surprising is that almost nothing has been spent on a better representation of the energy function. Not only that, in the original Raman and Stillinger waters, they had a 5-point water because they used lone pair orbitals. Nowadays we use a 3-point water, and that makes it 9 over 25 times faster, or 25 over 9, because it's the square of the number of particles. So it's kind of interesting that we haven't made things more complicated, and in some ways nothing bad has happened. But there's been a lot of fiddling with energy functions. Energy functions in proteins are now sort of calibrated on proteins themselves. It just seems like this approach is wonderful for the 1960s, but it doesn't sort of fit very well for the 2020s. So we need to do something different, and this involved a move away from this dead physicist energy function to functions, energy functions that include quantum mechanics. It turns out that in the USA at least, it is impossible to get any funding for anything except the good old-fashioned dead physicist energy function. It doesn't matter who you are. And one of the reasons is, and I'm quite angry about this, is that there's charm, amber, and NAMD, etc. And because these are all essentially the same, but they're considered independent, there's a very large number of people. Their community is way out of size compared to what they're actually doing, because somebody puts a feature into amber, the other group then puts it into charm, puts it into charm, puts it into NAMD. And all these programs are very heavily supported. This means that money is not ever given to anything that's going to go against that stream. So this work was actually done by entrepreneur Carrie Queen initially in Moscow in a company that was called Algodyne. It no longer really exists. But the idea was basically to use quantum mechanics to derive a force field. Varsha and Lifson could not actually measure the interaction of pairs of atoms. They could measure sublimation energies, crystal structures, etc., vibrations. Here, with quantum mechanics, which has come a long, long way, we can now calculate with surprising accuracy, say, the interaction of two water molecules at different distances apart. So the idea, which is a simple one, take two water molecules, put them into 1,000 different poses, calculate the energy at every single pose by a high-level quantum calculation, and then fit this with a force field. It turns out that you can do that, for example, for two methanes. Now, a good force field is one where once you've parameterized methane-methane and water-water, will correctly give you water-methane. And that depends very carefully on how you divide up the energy terms. And the group of physicists initially at Algodyne, and I was a consultant for them, I used to joke that they knew much more about hydrogen bombs than hydrogen bonds early on, but they got quite good at hydrogen bonds as well. They decided that they would break it up a bit like it was broken up by quantum mechanics in the 40s into electrostatics, exchange, induction, and dispersion. Each of these terms are parameterized separately. They're removing clouds. This energy function is about 20 times slower than classical terms, but we just got a factor of 10 to the 10. So 20 times should not be worrying you, but people are still, right now with simulations, it's like who has the longest one. And what really should matter is who's got the most accurate one. This is particularly important, this particular approach for drug design, because in proteins you can keep them parameterizing unknown structures. A new drug, by definition, is new, and you can't really calibrate its potential functions. So you need to be able to calculate them. Quantum mechanics in general doesn't really care what the atoms are. You can calculate this. We did a calculation, a test calculation using Algodyne. Subsequently, Algodyne is now involved, and Roger and I work together in a company called InterX, which again is privately funded, taking this thing further and trying to really use this as a way to define an energy function that can be used for drug design. Here's an example of some work that was done by Leonid Piroslavitz and Gaurav Chopra. They were both in my lab. Leonid is now with InterX. We took a quantum mechanical molecule, C60. So C60 is just 60 carbon atoms in a sphere. If this molecule is treated by the dead physicist energy function, it's only 60 carbons. There are no quadrupoles, no dipoles, no electrons, just spheres. If you put it in a quantum calculation, you have all those things. And what we looked at was C60 in a big box of waters and looked at how water is rearranged on the surface of C60. And in quantum mechanics, there's a huge difference compared to classical mechanics. The waters around C60 are much more ordered in a quantum mechanical calculation. So they're not the same, and there are problems with using it. I just wanted to end by mentioning that right now I have a small group who are working on lots of different things. I've always liked working on lots of different things, so we're comparing whole genomes, X-ray phase problem, cryo-EM on membranes, rubber dynamics, and so on. So different things. Okay. And just to say that we've now reached the end, and thank you all for your attention.
Your questions to the microphone so we can record them.
So when you were talking about, I didn't understand one thing when you were mentioning potential, knowledge-based potential determination. You're averaging over all crystal structures,
exactly.
right?
Now, I went through that rather quickly. Let me just go back to it. I'm glad you asked that question. I felt the same thing, but I sort of glossed over it. So in a knowledge-based potential, you average, you say you want to have an interaction between a particular pair of atoms. It could be, now the first thing you do is you have many atom types. You go well beyond the atom typing that's used chemically. So for example, the alpha carbon of valine is a different chemical type from the alpha carbon of leucine. When you do this, you end up having, I think, 180 atom types. It doesn't really matter because if you have enough protein structures, you can collect data. And actually, on this next slide, I actually show just how the data has grown on a logarithmic scale. The amount of data that existed when Shiraga and Tanaka did this has now been increased by a factor of 10,000. So you have plenty of data. These histograms can be very, very well occupied. So you just take every pair of atoms, connect a histogram for its distances, and then normalize. The normalization could be that it's an ideal gas. It could be that you've randomized all the labels. And you could just take a protein and say, okay, here the atoms are, just randomize the labels. There's lots of ways of normalizing. It actually matters. But let's just leave that aside. The important thing here would be, let's imagine two atoms were attractive. You'd expect what would happen, there'd be a lot of distances that are close, fewer distances in between it, and when you go very far away, you always have lots of distances because the number of distances from any point increases as r squared. So you certainly have to normalize by r squared. And then if you normalize this, you'd say, okay, this high attraction means there's a low energy here, and there's a high energy here, and then a low energy again. If, on the other hand, you had a distribution like this, where the number of values just increased like this, as you'd expect if there was no interaction or repulsive interaction, the energy function would look like this. Now, the energy functions are actually quite complicated. The spline fits, we use spline fits, everything would be differentiable. But it turns out they're not smooth, they're very rugged. And we don't really fully understand this whole area. But these energy functions do give you minima for any macromolecular system that are very close to the starting point. And in torsional space, that's difficult to find. So they are useful. There's another whole approach that I also should have mentioned. There's a way to do normal modes without even worrying about the energy function. And that is you choose an energy function which is defined to have a minimum at the X-ray structure. This was something that was done by Monique Thirion in the mid-90s. And it turns out that it's very interesting. If you have an energy function where the energy is any function you like of the difference in distance between where you are now and what the distance is in the X-ray structure, that forces the X-ray structure to be a minimum. That function, you don't do any minimization. You just calculate the second derivatives very easily and do simulations. And in fact, for most intents and purposes, those calculations give exactly the same results as you get with more complicated potentials. It turns out, I think, that these low-frequency motions, all they really care about is overall shape. And if I gave you a banana and said what's it going to be, it's going to have a motion like that, maybe a twisting motion. These basic motions are very, very simple properties of the overall shape. Yeah?
Actually, when you simulate the protein, you put it into the water. But actually, when we do experiments for protein are very sensitive, you have to put salt and everything. So we had observed in any case protein collapse.
Well, so in the calculations, you normally put enough counter-ions to keep the system neutral. So in the DNA, when we had 24 phosphate groups, we had a number of sodium ions to take care of that. The problem was much more difficult. Say you think about pH. So, one pH unit, if you have pH, say 6, that means there's one proton for 10 to the 6 water molecules. If your box has only got 1,000 water molecules, you can't even put one in. So there are stochastic methods of doing this. For example, if you ran lots of simulations, you could have an extra proton in one of the simulations. This stuff is still very difficult to do. And a lot of times what you do is you sort of assume the protons are there as false degrees of freedom, and they just neutralize things. So if you change the pH, groups that would be ionized are not ionized, and other groups that wouldn't be ionized are ionized. So you use the pK in that way. But I think that given all the problems with simulation, it's amazing how well they work. And I partially think it might be that we haven't yet asked the really difficult questions. I think drug design is a very difficult question because we care about energy differences of less than 1 kilocalorie. Whereas if you simulate the whole, if I showed you the motion of DNA and said, well, what's wrong with this? Possible to tell. If the whole thing comes apart, maybe bases are opening up too slowly. It's quite difficult. The important thing, though, is, and I think in some ways why simulations have become so popular, is it really is good for experimentalists to look at these movies. Just as and it's just good. And I think in many ways that's very easy to run a simulation. And even to look at these things, you can make movies like this used to be made, one frame a day and then one frame every 10 minutes. But nowadays they can be made in real time. So you can actually look at any of these things in real time, change your viewpoint, zoom in and out, and I think it just gives you a feeling of what's going on. Maybe like, gee, I didn't know that group was moving so much. Okay, and oftentimes the things that are very clear are usually independent of the details. Yeah, there's more questions.
In this equation, the motion space and then the distance should be correlated.
Yeah, so basically, essentially what you do is everything is correlated, but it doesn't really matter in an energy function. You just have to calculate the first and second derivatives, and that is lots of numerical messing around. But essentially what you do is you calculate the derivatives in Cartesian space, and then you convert them to torsional space with the Jacobian. It turns out for second derivatives, that's actually very expensive. So what we actually do is we do numerical second derivatives, but we use a wonderful trick that was discovered in the 60s. When you do numerical derivatives, you make an epsilon change. You take the energy, you add epsilon to all the variables in one variable, and get a new energy at f at x plus epsilon, and then you subtract the f of x divided by epsilon. Trouble with that is that if you have, say, 8 figures of precision, the derivative has only got the square root of the precision. But there's a trick to completely avoid that. You use your epsilon is a complex number, and many calculations can do complex arithmetic. So if you do all your calculations in complex arithmetic, you can get numerical derivatives to machine precision. The thing is, this was an idea which was invented by, it was actually invented by Clive Moller, the guy who founded MATLAB. But he actually forgot about it. And then somebody else rediscovered it in the 2000s and didn't even know that Moller's paper existed. And recently I saw a blog of Moller saying, yeah, he didn't even know he'd done it, but it's obviously very important. So, yeah? You stop when you want to stop.
Just repeat the question. Just repeat the question.
Yeah, if I can hear it. Go ahead.
We see in small life harvesting complexes that protein vibrations act like quantum harmonic oscillators. Two questions ahead. Where do you think the link between the classical theory and quantum theory lies? And the second, can you produce predictions of spectral density based on Austrian or normal mode?
Yeah, certainly, okay, so quantum mechanics is really important for high frequencies, if only because the 0-point energy is so many kilocalories. So basically, without any temperature, the atoms are moving as if they were at a super high temperature classically. Not only that, but bonds don't like to absorb energy quantum mechanically like they do classically. So this is wrong. And even in the work that I was talking about, about a quantum mechanical force field, we were still mostly thinking about doing classical dynamics. So the forces would be different, the dynamics would still be classical. I think that it obviously matters enormously. And I think that certainly in light harvesting systems and things like that, where you have tunneling and whatever, these things matter enormously. We still have to get there. I mean, one of the nice things is that computers keep on getting faster, and I guess the Earth will be around hopefully for a long time, so we will in the end solve these problems. But I think it's a hierarchical thing. I think that there are going to be all sorts of very interesting things. And I think right now what's interesting is just to even take simple theories of quantum mechanics and try to put them into non-homogeneous environments like proteins. You might find that there are paths in which things happen by some effect that is there in the quantum mechanics, but you didn't really emphasize, happen particularly quickly or whatever. So I think it's probably on a case-by-case basis of what matters. And I think often people ask me, are your calculations accurate enough to help me with this? And sometimes really inaccurate calculations can help people. For example, are these two groups from the same side of the molecule? Well, go to the PDB and look. But often if you give them a model with their sequence, they're going to feel much happier about that. Nothing is different from just looking at the PDB where the residues are. Are these things close together? So I think those things can be very important.
One last question.
Yes.
When we coarse grain molecule, and then we will have loss of degree of freedom. But was the entropic free energy dealt with can accommodate this?
Yeah, you're absolutely right that as soon as you as soon as you reduce degrees of freedom, and coarse graining is also reducing degrees of freedom, torsional angles, essentially you're averaging over other degrees of freedom. And they have entropy. And I don't know the effect of that. So I think that, again, I think we need to see. Entropy has been one of those things that, so what's interesting about entropy is that it's relatively easy to measure, but very hard to calculate. And it's only easy to measure because all experiments are done on 10 to the 18 molecules at least. Entropy is it's an integral that has to be averaged a great deal. I'm starting to wonder when people do more and more work on single molecules, maybe they're going to stop talking so much about entropy because it's just one of those things which, I don't know, somehow sometimes it's useful, but I don't think I found, I don't think entropy is a fatal flaw. I think we can deal with it in approximate ways. But I agree with you, it's a problem. But remember, we're looking at motion on a very coarse scale. And hopefully it'll average out, but maybe not.